If a discrete random variable can take several values, then it's convenient to record the probabilities of it taking those values in a table. And the table is called the distribution of the discrete random variable. There's actually two ways to make the table. So let's say we're given a random variable, let's say x, which can take values, so either, I want this to be a discrete random variable. So it can take only finitely many values, or maybe countably infinitely many. So it can take values, let's say a0, a1, a2, a3, etc. Possibly infinitely many of these, but we can list them. As shorthand for the probability that x equals one of these values, sometimes we use a little p. So p of ai means the probability that x equals ai, just shorthand for that. And this is called the probability mass function. Of x. And similarly, we could define, I'll use capital F of a sub I for the probability that x is less than or equal to that value. And I'm thinking of these as being ordered, so a0 is less than, a1 is less than, etc. This is called the cumulative distribution function of x. Now, either of the tables I, p of ai, so we can make a table with, let's say ai, so a0, p of a0, which is probability that x equals a0, a1, little p of a1, which is probability that x equals a1, etc. We could put all of these probabilities into a table, or we could have ai and capital F of ai, so a table for the cumulative distribution function. So a0, probability that x is less than or equal to a0, which is f of a0, and then a1, probability that x is less than or equal to a1, which is f of a1, a2, probability that x is less than or equal to a2, in other words f of a2, etc. Now, either of these tables is called the distribution of x. Now, maybe that could be slightly confusing because we've got two different tables here, and if I say distribution of x, I might be thinking of this, and if someone else says distribution of x, they might be thinking of that. But they're equivalent tables. If we have one table, we can get the other. So all the probabilities that we want are given by either one of these tables. So let me rewrite this notation more briefly so I can have a little bit of space. So little p of ai is the probability that x equals ai. Capital F of ai is the probability that x is less than or equal to ai. So I claim that either table gives the other. And that's because if I want capital F of AI, the probability that x equals less than or equal to a, the probability that x is less than or equal to AI, that's p of a naught plus p of a1 plus p of up to AI. So I can get this f of AI by summing a bunch of p of AIs, by summing up p of different values. And then what if I want p of AI and I'm given this cumulative distribution table? Well, if AI is the ith biggest value here, then I guess it's the probability that x is less than AI minus the probability that x is less than AI minus 1. Because the only element counted here is going to be, well, in this difference is going to be AI, because we're going to subtract off the probabilities of everything less than that. So in other words, if the possible values of x are, let's say, non-negative integers, 0, 1, 2, 3, 4, etc., then capital F of 4 equals probability of 0 plus probability of 1 plus probability of 2 plus probability of 3 plus probability of 4. And then probability 4, if we're just given f's, is going to be probability that x is less than or equal to 4 minus the probability x is less than or equal to 3. All right, so let's write out a probability distribution table. So for example, let x be the sum of two rolled dice. So we'll roll the dice and let x be the sum that we see. So the possible values that we could see are, we could see a sum of 2 or 3 or 4. Anything, 2 is the smallest, double ones, and then 12 would be the greatest. 6, 7, 8, 9, 10, 11, 12. And if we want to record the probabilities of these, there's only one way to get double ones. So 1 over 36, because there's 36 possible things that could happen if we roll the dice. Then there's two ways to get 3, 1 and 2 or 2 and 1. And there's 3 ways to get 4, 1 and 3, 2 and 2 or 3 and 1. And similarly, 4 ways to get 5, 5 ways to get 6, six ways to get 7, and then again there's only 5 ways to get 8, 4 ways to get 9, 3 ways to get 10, 2 ways to get 11, and 1 way to get 12. So this is a table of all the probabilities that we need if we're wondering what happens to the sum of the two dice when we roll them. The sum's going to be 2 through 12, and these are the probabilities of seeing those values. And while we're at it, why don't we make a table for the cumulative distribution function. So this is the probability that x is less than or equal to I. So the probability that x is less than or equal to 2 is just 1/36, because that's the smallest value possible. The probability that x is less than or equal to 3 is 2/36 plus 3/36. sorry, 2 plus 1, which is 336. And the probability that we have a sum less than or equal to 4 is the sum of all these three, so 636. 4 plus 3 plus 2 plus 1 is 1036. 1536 for the probability being less than or equal to 6. 15 and 6 is 21. 21 and 5 is 26. 26 and 4 is 30. 30 and 3 is 33. 33 and 2 is 35. 35 and 1 is 36. So of course the probability that the value of x is less than or equal to the highest possible value has to be 1, because all the values are less than or equal to the highest possible value. So the cumulative probability function, the cumulative distribution function column is always increasing from the probability of seeing just the lowest possible value all the way up to 1 for seeing less than or equal to the highest possible value. The individual probabilities themselves, in this case, they go up and then go back down again. They could be anything. They could be any numbers that add up to 1 and are positive. But if we take partial sums, the partial sums are always going to start low and then end up being 1. Our last partial sum is going to be 1. All right, let's do an example with infinitely many values. Now, if the random variable can take infinitely many values, countably infinitely many, it might be better to have a formula than a table because, well, we don't want to write an infinite table. So formulas for the mass function and the cumulative distribution function can be useful, especially if the random variable can take infinitely many values. So let's go back to the problem where we roll a die until we get a 6, because there's infinitely many possibilities for how many rolls it could take to get that first 6. So we're going to roll a die until getting the first 6. And let's let x be number of rolls required. So we can start making a table. Maybe if we start making the table, we'll see what the formula should be. So little p of I is the probability that x equals I, the probability that we see our first 6 on the ith roll. So the earliest we could see the 6 is the first roll, and that'll happen with probability 1/6. And we could see the 6 on the second roll, and that'll happen if we get something besides 6 and then a 6. Get something other than 6 with probability 5/6 times 1/6. And then we could see our first 6 on the third roll, and that'll happen if we fail to get a 6 and fail to get a 6 and then succeed in getting a 6. We could see our first 6 on the fourth roll, and that'll happen if we fail to get a 6 3 times and then get a 6 on the fourth try. And we could succeed on the fifth try, which happens if we fail 4 times and then get a 6. And by this point, or maybe even earlier, we can see what the formula is. So to succeed on the ith try, we need to fail I minus 1 times. So 5, 6 to the I minus 1, and then succeed on the ith trial. So fail I minus 1 times, succeed on the ith trial. Right, and it turns out that there is a nice formula for the cumulative distribution function also. So let's find a formula for capital F of I equals the probability that we take I or fewer trials to see the first 6. So I claim that this is 1 minus 5, 6 to the I. So I guess we could sum up the probabilities that we see the first 6 on the first row plus the second row plus the third row plus the probability of seeing it on the third row, etc., all the way up to the probability of seeing it on the ith row. Add those together. But I actually found that it was easier to subtract. So the probability of needing I or fewer trials is 1 minus the probability of needing I plus 1 or more trials. So let's look at the probability that we need I plus 1 or more trials to see the first 6. To see the first 6. So I guess we fail on the first roll, and we fail on the second roll, and we fail on the ith roll. And actually, if we fail on the first I rolls, that's the same as guaranteeing that the first success happens on the I plus first or later roll. So it's just 5, 6 to the I. So we want to subtract this from 1, and that's the formula we have there. 1 minus 5, 6 to the I. All right, now let's do one more example. It's a little different from these, using discrete random variables and their distributions. So for example, let's say we have 20 cards labeled 1 through 20. Let's choose 4 of them, and let's let X be the largest chosen one. So I guess X could be as small as 4, because the smallest cards we could choose are 1, 2, 3, 4. The largest of 4 cards couldn't possibly be smaller than that. And of course the 20 could be the largest also. Anything between 4 and 20 is good. So I think I don't want to make a table for all 20 values of the probability that X equals I. Actually, 17. 1 through 20 except for 1, 2, 3. But I don't want to make those 17 lines in a table either. So let's see if we can find the mass function, the probability mass function P of I is the probability that x equals I, and the cumulative distribution function capital F of I, the probability that x is less than or equal to I. Let's see, P of I equals, how could the biggest number be I? Well, I guess the lower three numbers have to be between 1 and I minus 1. So that is I minus 1 choices. So we'll choose three of the cards between 1 and I minus 1. And then choose the I. And that over the total number of ways to choose 4 cards out of 20, which is 20 choose 4. So this again is, we're going to choose 3 cards from 1 through I minus 1. And then we're going to choose I in exactly one way. That'll be the largest card. And 20 choose 4 is the total number of ways to choose 4 cards out of 20. Okay, so this fraction, of course we can erase the 1, is our probability that the largest card is I. Now let's check out the probability that the largest card is less than or equal to I. So we could add this up for I, for that number equals 4 up to I, but there's an easier way to do it. So the probability that x is less than or equal to I is, let's see, the number of ways to choose 4 cards so that the largest one is less than or equal to I. So I guess all 4 of them are going to be less than or equal to I. So we'll choose 4 cards from 1 through I. And then divided by 20 choose 4. And this will be the number of ways to choose any 4 cards out of the 20. So that's a formula for our cumulative distribution function, the probability that x is less than or equal to I, or as we wrote it before, capital F of I. Alright, now at the beginning of the lesson I called this the distribution of a discrete random variable. I left out continuous. That's because we're going to have a little problem with continuous random variables. Let's do an example and see what the problem is. Alright, so let's do the same example we had before. Let's choose a point x naught, y naught in the square bounded by x equals 0, x equals 2, y equals 0, y equals 2. Let's let z be the sum of the coordinates, x naught plus y naught. The probability that z equals 1, or if you like little p of 1, equals, so all the points where the coordinates add up to 1 are the ones on this line. Because this is the line x plus y equals 1. X coordinate plus y coordinate equals 1. The problem is that this line segment here has area 0. So if we compute area of line segment over the area of the whole square, which is 2 times 2, which is 4, we get 0. So actually for any value here, whether it's the area of this line segment or the area of that line segment, all of these line segments have area 0. So we're going to get 0 every single time for every single possible value of this random variable. So the continuous random variables really do behave differently, and we're going to have to treat them differently. Now if we look at the cumulative distribution function, that makes sense. In fact, last time we computed the probability that z is less than or equal to 1. We said that's the area of this region divided by the area of the whole square. So it's 1/2 the area of this triangle divided by 4, which we said is 1/8. And actually, if k is a number anywhere between 0 and 2, here's the line x plus y equals 2. So for k between 0 and 2, we have capital F of k, the probability that the coordinate sum is less than or equal to k is the area of some triangle here divided by 4, the area of the whole region. And the triangle, let's say this is k right here, x plus y equals k is this line. So this triangle is going to be a right triangle with leg lengths k, and the hypotenuse k squared to 2, but that's not important. And the area is k squared divided by 2. So k squared divided by 2 all over 4, so k squared over 8. Now if k is bigger than 2, then we're going to be looking at this line that hits the x-axis outside of the square. X plus y equals k. So we're going to want the area of this region, which is not exactly a triangle. It's the whole square, except for the part of the triangle that's not shaded here. So I guess we're looking for 4 minus the area of this white triangle divided by 4 to get the shaded area over 4. So if k is between 2 and 4, then capital F of k, probability that x is less than or equal to k, is the shaded area over 4, which is 1 minus the white area over 4. So we need to figure out what is this length here from this point to that point, because the area of the white region is that thing squared over 2. So let's figure it out. So if we make this line go down to the x-axis, then k now is the distance from the origin to there. That's k. And we know that this part is 2. So this part over here I guess, is k minus 2. No, this of course is a right triangle where the two legs are equal. So this is k minus 2 there also. K minus 2 plus something equals 2. And that something is going to be 4 minus k. Because if we add 4 minus k and k minus 2, the k's cancel, we get 4 minus 2 equals 2. So 4 minus k is this length. So we got 1 minus 4 minus k squared over 2 over 4. 4 minus k squared, of course, is the area of this whole square, but we only want half of it for the white part. So that's 1 minus 4 minus k squared over 8. Over 2 and over 4 make over 8. So actually the cumulative distribution function makes sense for continuous random variables, even though the probability mass function doesn't make sense. It's always 0. So the combination of these two is the answer. Maybe I should write them together. So it equals this if k is between 0 and 2, and it equals 1 minus 4 minus k squared over 8 if k is between 2 and 4. So for continuous random variables, the probability mass function is always 0, but the cumulative distribution function still makes sense. It's going to be area of a small region over area of a big region, probably. So for the first part of the course, for the next part, when we're looking at random variables, we're mostly going to work with discrete random variables, since the continuous random variables behave so differently. The end.